My name is Ashley, and this is my Lab 5. In this lab, we're analyzing the importance of air resistance in predicting an object's motion. We took something with very low air resistance, in this case a raisin box, and dropped it. And as you can see, this motion is very consistent with gravity, and it's almost completely due to gravity. It has very little air resistance. And then our object with a larger surface area, in this case a Dixie bowl, falls much slower and with much more inconsistency, although we'll find in this lab that it's not due to inconsistency, it's all due to air resistance. I took both of these sets of points and imported them into an Excel file, as you can see here. My slow object is indicated by these blue diamonds, which are much flatter than my fast object, which is indicated by these blue diamonds. I then tried to model these with Python, and I went over Python more in my last video, but I'll go over some of the very, very basics again. So I put in my mass and my position vector, and in this case, I only did gravity, so there's no air resistance. And you can see that this predicts the exact position of the raisin box. And then I took these in the CSV file from this and imported this as well into Excel, and you can see that shown by the red. I then played with the air resistance because obviously there is some air resistance, even if it's very, very small. And you can see that air resistance, which I predicted to be about 0.001. You can see this last point here is very close together. And so all those are very, very close because there's almost no air resistance. In my bowl, however, the Python model was a little bit more complicated. To predict the drag, you can see in the Excel spreadsheet that the gravity is in the same motion as it was in the raisin box, because as we know, mass doesn't affect gravity. And then here, you can see the results of my Python model, which, if I run it, I put in my air resistance here, which I approximated to be about 0.027, and that drag is negative. The bowl's negative velocity times that constant of proportionality, which, as I said, was 0.027. And then when I run this, it predicts almost exactly the motion of that bowl. You can see that motion here. And then the air resistance is this arrow pointing back up. So I then took the CSV file and put this in, and as you can see, it's very close to my tracker file. The green line here shows my gravity plus drag. So the question is, what does it mean? So when looking at these, when thinking about gravity versus gravity with drag, the gravity with drag is what's going to predict the terminal velocity, because this velocity is very dependent on how much surface area there is and how much air is going to be pushing back up on the object. You can see that it reaches it around this point here. It starts to level back off, and that's where it's hit its terminal velocity. So what if we were to throw the ball down, or throw the bowl down? I modeled this with Python here, and this is shown here. And so throwing the ball basically makes the ball reach, or the bowl reach its terminal velocity much quicker than were I to just let it go. So this blue line shows just letting the ball go, as I showed before, and this red shows if I was to throw it down with the drag included, and then the green, again, is much further off because it's not including drag, it's just gravity. You can see that this red line is what predicts the terminal velocity. Thank you.